Hi, everyone. Good evening. Welcome to Sense of Place. My name is Sarah Fox, and I'm so excited that you are able to join us virtually tonight. Tonight, we are going to be learning about debris flows from Mount Adams and Mount Hood with Dr. Richard Iverson. Dr. Iverson is a scientist emeritus with the U.S. Geological Survey. He was with them for 34 years at the Cascades Volcano Observatory, which is in Vancouver, Washington. And what he focused on was looking at the dynamics of landslides and debris flows, looking at how they function and how they move. But he had a specific emphasis on looking at sort of the downstream hazards of these flows coming off the volcanoes, the Cascades. And I think that's particularly important for us here in the Gorge, since we are all potentially downstream of the Cascades and potential slides. And when I first spoke with Dr. Iverson many months ago, he suggested that maybe a fall or winter lecture would be a good time for him to talk, since this soggy time of year is when these slides frequently get triggered. And for many of you, if you've been paying attention to the news, you know that our neighbors to the north in British Columbia have faced just this last month with a number of massive slides. And for any of you living here in the Gorge for any amount of time, you've probably lived through I-84 or Highway 14 being closed at some point due to a slide. So this is one of those topics I think sometimes we may not notice or think about all the time, but it is under our feet literally. And I'm excited to learn from Dr. Iverson tonight more of how he looks at the landscape, what it is and what it might become. So more on that. Let's see. For those of you who are new to Sense of Place, this is a lecture series that has been going for 12 years here in the Columbia River Gorge. The upside of being virtual due to COVID is we've had folks tuning in from all over the country. So I feel like I need to let you know where we're located is here in the Gorge, in Hood River, specifically is where we do our live events when we're live. And it's sort of premised on a simple idea, which is how do we bring together a lot of different people with a lot of different backgrounds and a diversity of topics and put them all in the same room. And the way that we did that is to say, let's use place as our focus and consider the cultural and the natural and the political history of this and all the different ways that we can look at this place. And then let's bring in amazing folks like Dr. Iverson tonight, or Dr. Jocelyn Akins, who we had last week, or Michael Bugh the week before, and have them share with us their expertise and the way that they know this place in a unique way. So this is our 12th season. If you didn't know already, we also have a companion podcast called Here in the Gorge, and it's been going, I think, about 5 or 6 years now. And Here in the Gorge, if you're not familiar with podcasts, is basically audio documentaries. So stories for your ears that you can listen to while you're making dinner or folding the laundry or driving to grandma's house during the holidays. And we've been able to use that format to dig really deep into stories of this place, including some of the unique Japanese history here that we have, mountain search and rescue, tribal fishing, a story about Woody Guthrie and why he came here and wrote songs about the dams back in the day. So maybe sometime during this holiday, you can tune into that when we're not around and still be learning about the Gorge. You will also, you should know that we're 12 years old. And the only way that a small lecture in a small area lives to be 12 is because we have awesome sponsors. And I can tell you, I don't think they're in it because we do advertising for them and make them tons of money. I know from knowing them that they're in it because they really care about this place. And this is one way that they're able to help their community and this place thrive. And so I hope when you look on the screen here, I'm guessing you'll see businesses or people you recognize. And should you see them on the sidewalk or stop in their business, I really hope that you'll take a moment to just say thanks, either with your mouth or with your money, because year after year, we are able to do this because of the people that you see on your screen right now. Lastly, I want to tell you about Mount Adams Institute. And we are one of many programs that Mount Adams Institute has. You'll see those listed on the side, the vets work, the public land stewards, the summer camp. And they are working to take all different sorts of people, from rowdy kids like my two daughters, to vets, to people who want to go on big crazy hikes and be adventurous, to folks who are going to connect with nature in a way, maybe like tonight, listening to someone like Dr. Iverson. They're saying, how can we help this diversity of people connect to the natural world in a way that works for them? And they are a great nonprofit. If you don't already know about them, after the show, scoot over to their website and you can learn more, because they may have other ways for you to connect to this place. With that, I want to invite Dr. Iverson on screen. And while he is tuning in and tuning on, I want to remind all of you, hi, Dr. Iverson, that we will have Q&A after the talk tonight. So if we're going along and you hear Richard say something that you think, oh, that makes me wonder about this, or have a question about that, go down to the bottom of your screen, type it in the Q&A box. And at the end of his talk, we will be able to come together and get through as many of those questions as we can. So don't be shy, put those in the box. And I think that's it. So take it away. Thank you so much, Dr. Iverson, for joining us tonight.
Thank you. Should I go ahead and share my screen?
Go for it.
All right. I hope everyone can see that all right and hear me all right. Sarah, let me know if that's not the case. So
you look good. You look good.
All right. Well, thank you for your introduction. And it's a real pleasure to be giving a presentation for the Sense of Place series. I actually didn't realize it had been going as long as 12 years, but I think it makes a really important contribution to the community here in the Gorge, and I'm pleased to be part of it. My subject tonight is debris flows, which are a common and to me very fascinating phenomenon. In fact, they're so fascinating that I've spent much of the past 40 years trying to understand their physics. Many of you might be relieved to know that tonight I'm going to talk almost not at all about physics of debris flows. Instead, I'm going to focus on what we know about debris flows from our local volcanoes here, Mount Adams and Mount Hood. So my talk will have 4 basic themes, and I'm going to begin with some real background material, sort of what is a debris flow, what causes them, why are they common downstream from Cascade volcanoes. I'll then talk about historical small debris flows, and small is a relative term here. I'm defining that as less than 1 million cubic meters. But these are flows that occur fairly routinely on Mount Adams and Mount Hood and are typically triggered by rainfall and/or snowmelt. I'll then move on to talking about prehistoric larger debris flows from the 2 volcanoes. And these are sort of a different animal altogether, in that they're usually not influenced so much by weather events, but rather they're triggered by large landslides or volcanic eruptions. And then finally, I'll talk about how we use models to help us anticipate the behavior of future large debris flows, or as we typically call them, lahars, which is that Indonesian term for debris flows that originate on volcanoes. So as far as what is a debris flow, you know, it's a well-known truism that a picture is worth 1,000 words, and I think a video is probably worth 1,000 pictures. So what I'm going to do is show you a video clip here of a debris flow that was taped in Indonesia, actually downstream from Semeru volcano, which has been in the news lately because it's been erupting lately with some pretty devastating effects. But this is a video that was shot 15 years or so ago by some French researchers, and it gives you a real good sense of just what debris flow is like.
Tu peux te pousser, monter un tout petit peu s'il te plaît?
So I think I personally probably wouldn't have cut it quite as close as the videographer did there, but nonetheless, he got some incredible footage. And what you really saw there is the fact that debris flows are, they're mixtures of mud, sand, gravel, boulders, sometimes boulders as large as small houses, transported in a muddy, water saturated matrix. And debris flows have some really interesting characteristics in the sense that they can flow almost as fluidly as water, as you saw there, that from a distance really didn't look so different from an approaching flash flood of water. But in fact, they're actually more than 50% solids by volume. So typically about 60% solids by volume. And so as a consequence of that, debris flows have a density that's comparable to that of concrete. But again, they can flow almost as fluidly as water. And that's what makes them such devastating hazards and also big agents of geologic change. So I'm going to start by kind of talking about some real basic geological background material and use this good example here of Upper Newton Creek Canyon on Mount Hood. This is on the east side of Mount Hood, and I'm sure many of you have been to this exact vantage point. Looking at some of what you can see from this vantage point, first over here on the left, and I hope you can see my red cursor here. On the left, this ridge, which goes by the informal name of Pea Gravel Ridge, consists of loosely packed material, a combination of glacial till and volcaniclastic deposits, meaning fragmental debris that was erupted from the volcano. And so everything here is loose. The slope is steep. It stands at more or less the angle of repose, meaning it's about as steep as it can be for static material. And then there's more loose debris over here. Up above this loose debris, you see some outcropping lava flows. And much of the volume of Mount Hood and of Mount Adams is made up of lava flows, but those lava flows are interspersed in places by layers of this looser volcanic material. And that layered structure is why we refer to these volcanoes as stratovolcanoes. They're made up of these stratified layers. Upslope from the lava flows here, we see Newton Clark Glacier, what's left of it anyway. Obviously, it was much larger in the not too distant past, but it's still a glacier. And then up above the glacier, we see this outcrop of yellowish looking rock here. This is hydrothermally altered volcanic rock. And what I mean by hydrothermally altered is that acidic fluids circulating within the volcano, either gases or liquid, actually change the minerals in the rock. And they often will convert relatively hard, dense minerals, things like plagioclase, into looser, weaker minerals, clay minerals that can hold more water and that have a lower density. And so that has the effect over time of weakening that rock. And as a consequence, those areas of weakened rock can spawn landslides or debris avalanches. The Timberline Trail comes through right over here on the right-hand side of the frame. And so a lot of you no doubt have walked right near this location. So looking at this accumulation of loose debris over here on the left, you can see here some scars on the slope, and these are sources of recurrent rain-triggered debris flows. Newton Creek Canyon probably has as many debris flows as any individual canyon on Mount Hood. And most of those debris flows start here in the upper canyon. They can involve water spilling over the cliffs here, but much of the sediment comes from these landslides, these landslides alongside the channel. And it's the mixing of the water with that sediment on these very steep slopes that transforms the mixture into a debris flow. Then if we look up in this location, again at this hydrothermally altered rock, you can see this band of yellowish material here extending down from that source area. These are deposits of recurrent small debris avalanches, basically avalanches of weak rock fragments and ice. Usually they do contain a fair amount of ice. And they've recurred here frequently, even during the last several decades. The last notably big one was back in 2001. And when you see these kinds of yellowish deposits draped over the topography on any of the volcanoes around here, that's a good indication that what you're probably looking at is a debris avalanche deposit. And one thing that makes them sort of curious is the way they do drape over the topography. A reason they do that is that typically when they occur, they do have a large content of ice. And so if you were to look at the deposit right after it happened, it would look quite different from this. But over the years, the ice melts away and you're left with this sort of pancake of yellowish debris, showing you the track of where the debris avalanche occurred at some time in the past. So debris avalanches are a particularly big deal on Mount Adams, and particularly on the west side of Mount Adams. This source area here, which is the head wall of the White Salmon Glacier and of the Avalanche Glacier, repeatedly spawns debris avalanches, generally relatively small ones. The biggest one in historical time was back in 1921. But we had this fairly large one in 1997, August of 1997, that was big enough that the avalanche debris spilled over the top of the moraine here of the Avalanche Glacier and ran down into some drainages, the Cascade Creek drainage, the Salt Creek drainage, and did spawn some small debris flows that issued from the distal end of the debris avalanche. Again, you see the yellowish character of this material, which is indicating that a lot of this is rich in these hydrothermally altered weak rock type minerals. And you also see older deposits here of that same yellowish material. That's from older debris avalanches in the same location. If you look at this photo on the left here, this shows what one of the lobes of this deposit looked like a few days after it occurred back in 1997. And the thickness here in a lot of places was 15 to 20 feet. And yet, if you visit this same site now, all you'll see again is this thin pancake deposit, what's left behind after all the ice melts away. In that same year, in 1997, there was a more photogenic debris avalanche that occurred on the east side of Mount Adams, and I refer to that as the Klickitat avalanche because it crossed the Klickitat Glacier here. What was interesting about this event is that instead of occurring from some of this very weak material, of which there's a great deal near the summit of Mount Adams, it actually occurred in a relatively hard rock area on a prominence known as the Castle. And as a consequence, this debris avalanche, although it too entrained a lot of ice from the glacier, it really showed little tendency to transform into a debris flow at its distal end. So it was more of a classic pure rock avalanche. The sorts of events that we're really concerned about from the standpoint of volcano hazards and big lahars, big debris flows downstream volcanoes, are exemplified by this event that occurred rather recently up in British Columbia at Mount Meager volcano, which is about 100 miles north of Vancouver, BC. It's at the very northern end of the Cascade range of volcanoes. And it's also in a very remote, uninhabited area. And so even though this event was quite a big deal geologically, it really didn't receive a great deal of public attention, at least not in this country. But what happened is that without any provocation, without any weather event or triggering earthquake or anything notable like that, a 50 million cubic meter landslide occurred here on the south side of Mount Meager and removed the entire south flank, transformed almost entirely into a debris flow in lahar, and traveled down this sinuous channel of Capricorn Creek and then into the floodplain of the Lillooet River. And it inundated the entire width of the Lillooet River floodplain and sent a flood wave downstream from there. Again, fortunately, nobody was killed or injured in this event. It occurred in the middle of the night also, and did provide quite a scare to some campers who were not too far away. But again, it was in a remote setting. But it's the sort of thing, if it were to happen at one of our local volcanoes here in the Cascades that has a higher population density around it, it would be quite a disastrous sort of event. So thinking about debris flows at the Cascade volcanoes, it is really important to recognize that they span a very broad range of sizes. And here I'm showing seven orders of magnitude. And by order of magnitude, I mean powers of 10. So each one of these is 10 times bigger than the one that precedes it. Very small debris flows, rain-triggered debris flows, occur pretty much every year on Cascade volcanoes. Many of them go completely unnoticed because they're in remote wilderness type settings. And those are things that involve just a few thousand cubic meters of material. If we go slightly up the scale, then events have the potential of actually becoming hazardous and even deadly. In fact, this relatively small debris flow of just a few tens of thousands of cubic meters was actually a fatal debris flow that occurred on Mount Hood. It came down the Palali Creek channel. There was someone camped at the Palali campground at that time. Their camper was destroyed, and the East Fork Hood River was also dammed by this event. So even though it was fairly modest and was a storm-triggered event, it had real consequences. A larger rainfall-triggered debris flow was the Mount Hood Elliott Branch debris flow that was one of many that occurred in 2006. And I'll return to this and talk about it in some detail later. Stepping up the size scale, we can go to these Mount Adams avalanches, these recent ones in 1997, which again were not debris flows, they were debris avalanches, but they fit neatly into my size scheme here. Then we can look at the Mount Meager, British Columbia event. That's 10 times bigger still. Mount St. Helens, 1980. This is actually the lahar, the size of the lahar that flowed down the North Fork Toutle River as part of the eruption sequence of events at Mount St. Helens in 1980. The landslide that occurred at Mount St. Helens at that time was far larger than the size of the lahar. It was more of this scale. This bar represents a prehistoric lahar that occurred at Mount Rainier about 5,600 years ago, the famous Osceola mudflow or Osceola lahar. It was several cubic kilometers in volume, inundated a vast area, and it's actually one of the world's larger known lahar deposits. And again, I'll just make the point in passing that in the Cascades, we've developed a habit of reserving the term lahar for only large debris flows. And generally these smaller debris flows we refer to simply as debris flows in order to avoid confusion. So there have been lots of these smaller storm-triggered debris flows at Mount Adams and Mount Hood over the decades. And again, by smaller here, I'm referring to things that are typically less than 1 million cubic meters in volume. Here's a table summarizing some of the recent notable debris flows at Mount Hood. This is from a period from 1980 to 2005, and these data were compiled mostly by Tom DeRue of the Forest Service. And within this table, which is ordered chronologically here, you'll notice that I've used a bold font to highlight some of these events or locations. And these are all locations or streams that feed into the Hood River system. So you can see that really the preponderance of debris flows that have occurred on Mount Hood, of storm-triggered debris flows, have fed into the Hood River drainage system. Another pattern that you'll see among these events is how the great preponderance of them are in the fall, especially October, November, December. That's, of course, when the rainy season usually begins in earnest. And also importantly, it's usually a circumstance where there is not yet a heavy snowpack at the higher elevations. Most of these do start at quite high elevations, typically around 2,000 meters or 6,600 feet elevation would be kind of typical. So above tree line, up in the area where there's lots of steep, loose debris around, that's critical to provide the source material. But later in the winter, as these elevations are covered by a heavy snowpack, heavy rainfall, even the so-called pineapple expresses, these warm, very rain-rich storms that move in from the South Pacific, even those are relatively unlikely to trigger debris flows high on the volcanoes midwinter, simply because the heavy snowpack is present. And that heavy snowpack acts as a sponge, basically, that absorbs a lot of that rainfall and holds it for a period of time and allows it to gradually, sort of leak out through the bottom of the snowpack. But it doesn't really get into the ground rapidly because of the sponge-like effects of the snow. On the other hand, if there's just a little bit of snow on the ground, the rain simply melts that snow, and that's more typically the circumstance in the fall. So now I'm going to move on to the rather dramatic events of 2006, where we had lots of debris flows, storm-triggered debris flows, up and down the Cascades, all the way from Mount Rainier in the north to Mount Jefferson in the south. Every volcano experienced a large number of debris flows during this storm event. And on Mount Hood, there were 7 of them. They all originated at elevations above 6,000 feet. And as you can see, there were 4 of them that flowed down drainages that ultimately enter into the Hood River system. This, by the way, comes from a study done as a master's thesis at Portland State University. And there was a companion master's thesis done on Mount Adams. And Mount Adams, too, experienced a total of 7 notable debris flows as a consequence of that one storm event. And an interesting difference between Mount Adams and Mount Hood is that these flows all started at slightly higher elevations than the flows on Mount Hood. These tended to start elevations above 7,000 feet as opposed to 6,000. And that's simply a reflection of the difference in the geology or the geomorphology of Mount Adams and Mount Hood, and the vegetation as well. Tree line on average is a bit higher on Mount Adams than it is on Mount Hood. The great abundance of steeply sloping loose debris tends to be at higher elevations on Mount Adams than it is on Mount Hood. And so basically the storm was simply, it had to have access to that kind of debris to provide the material to get the debris flows going. An interesting aspect of that storm in 2006 was that the rainfall was so dramatically influenced by elevation. So during this period of heavy rain, whereas lowland elevation, similar to that, say, of most of the lower Hood River Valley, about 500 feet, received something like 5 inches of rain during that time. At higher elevations, up at 4,000 feet, it received more than a foot of rain. And at the same time, all that rain was falling, snow was being melted, particularly from the higher elevations above 6,000 feet. So these are data from the Timberline Lodge gauge that are archived by the Northwest Avalanche Center. And what it shows here, if you look at the black dots, these are daily rainfall totals measured at that gauge. So you can see some days with a heck of a lot of rain, 4 inches on some days, especially the peak day of November 7th. But at the same time, all that warm rain was falling, the snowpack was melting. The red line here shows the depth of the snow. Started out at about a foot deep at that gauge, and by the time we reached November 7th, the snow was all gone. And that too contributed to the big input of water that triggered all those debris flows at those higher elevations. Another interesting aspect of this, or a somewhat frustrating aspect for those of us who are interested in studying these debris flows, is that right after all those debris flows occurred on November 6th and 7th, the weather turned colder and snow started to accumulate rapidly. And so very quickly, all the evidence was buried under snow at the higher elevations as to what exactly had happened. And so it really wasn't until the following summer, when the snow melted, that we were able to see better what had happened. And so one place that we tried to do a fairly thorough investigation of was this Elliott Branch Middle Fork Hood River debris flow, which was the most important one, I think, that occurred on Mount Hood. There was also a very important one on White River and actually Newton Creek as well. They did a lot of damage to the highway. But this one was really the biggest of the bunch. It was about 500,000 cubic meters, best estimate. And Darrell Lloyd made this very beautiful panoramic photo of this deposit of the flow just above Lawrence Lake Road. So one thing that, again, we didn't really learn about this flow until the next summer, when we were able to get out and look at the evidence, was where exactly most of the source material came from. One way you can look at that retrospectively is to look at these before and after Google Earth oblique images of the area where it came from. This is the kind of, for reference here, here's Cloud Cap Inn up on the north side of Mount Hood. Here's the most distal part of the Elliott Glacier, which is covered in debris here, but this is ice cored material down to about this elevation. And what you can see here, if you study carefully the difference between the before photo and the after photo, as you can see that there are some big scallops that were taken out of the terrain right in this area. You can see the scallops here. You can see removal of quite a bit of vegetation. There's also a scallop on this side that's a little less visible. And you can see, a channel coming down here from the toe of the glacier. So what was visible in the field when looking at it close up is that there was some speculation that some of these events might have actually been glacial outburst floods, but really I think that was a minor contributor to where the debris flows came from. Undoubtedly, there was water rushing out of the toe of the glacier, and undoubtedly there was gully erosion here. But these landslides adjacent to the channel of the Elliott Branch were really quite large and dumped a huge amount of debris into the creek. You can judge the scale here by looking at the size of these full-grown Douglas fir trees here in the background. This is a pretty good sized landslide, and similarly, this one on the East Moraine was a big slide too. So really, these were events that originated as landslides in loose debris, which is the real typical scenario on most of these rain-triggered debris flows. A few key downstream areas pertinent to the Elliott Branch debris flow. First of all, here's the Lawrence Lake Road depositional fan, which doesn't look too large on this image, but is pretty spectacular when you're out there standing on it. And that's still readily visible today if you drive out to that location on the way to Lawrence Lake. Once the debris flow spread out on this fan, it then got funneled into a narrower constricted channel here, joining forces with other tributaries and forming the Middle Fork Hood River. And the channel here is constricted by the presence of this Parkdale lava flow. And so throughout this reach, the debris flow continued moving as a debris flow, but it really didn't leave a great deal in the way of deposits. However, once it escaped that constricted area and started to have an opportunity to spread out, it really started leaving deposits here again in the vicinity of Red Hill Road and took out the bridge there. And then finally, when the debris flow traveled as far as the confluence with the West Fork Hood River, at that point, there was enough additional water coming in from the West Fork that the flow transitioned from being a debris flow to something that we would call a hyperconcentrated flood. So basically just a water flood carrying a whole lot of sediment. And of course, a lot of that sediment ended up in the Columbia River and greatly enlarged the spit at the mouth of the Hood River, the spit extending out into the Columbia. The flow was erosional. The debris flow was erosional until it reached that Lawrence Lake fan. So here you can see the mouth of the canyon that it discharged from. An interesting thing that was visible after that flow had passed and had caused a lot of erosion in this canyon is you could walk up and you could see deposits from older debris flows. These are very conspicuously debris flow deposits here. Hard to say exactly how old they are, but unquestionably, this is a recurrent sort of event. And I think it's likely that Lawrence Lake Road fan is composed almost entirely of debris flow deposits. This is another interesting and characteristic feature of debris flow deposits, and this is just above the location of where the Red Hill Bridge was taken out by the debris flow. The flow left this very conspicuous lateral levee here of boulders for the most part. And this is a feature that you'll find in many places where debris flows have traveled and had the opportunity to spread out laterally a little bit. In fact, if you're hiking around in the mountains here, up above tree line, you can see a lot of these boulder levees along channels of all different sizes. You'll see them alongside very small channels that are only a meter or so wide. And in that case, the boulders aren't so big. They're probably more like softball size. But in any case, when you see those levees stacked up along the edge of channels, those were put there by debris flows of various sizes and at various times. If you go to this site now, if you go to the Red Hill Bridge crossing now, this doesn't look like this anymore. It doesn't look like this at all. In fact, the Hood River, the main channel of the Hood River here, the Middle Fork Hood River, has shifted so that it now flows over here. It shifted substantially to the east. I think it's also likely that I don't know this for sure, but my speculation is that in the course of rebuilding the bridge and doing road work and so forth around there, I think a lot of these larger boulders ended up getting moved. And so Unfortunately, even though this is a very classic looking sort of deposit here, it won't look quite like this if you go and visit the site now. Okay, so I'm now going to move back to Mount Adams. And if you want to visit some of these sites in the field, certainly the easiest ones to reach are those on the west side of the mountain where the access is better. The Salt Creek flow, the Lewis River flow, the Adams Creek flow, their impacts are all still readily visible today. Although the Lewis River or Lewis Creek flow was considerably smaller than the other two, and so it's less dramatic. The one that's easiest to look at is the Salt Creek debris flow. And here's a Google Earth oblique overview of the path of that flow with some geographic markers. So the flow again started from shallow landsliding, in this case up in the moraine of the Avalanche Glacier up in this area. And some of these moraines are ice cored, and that's true at Mount Hood as well. Many of the moraines around the perimeters of the glaciers have layers of snow and ice buried within them, and that makes them particularly vulnerable to shallow landsliding. The flow, once it got started here, traveled down Salt Creek, and then interestingly, at this location, some of it spilled over, overtopped the channel and spilled over into Crofton Creek. And so there was a secondary debris flow that traveled down Crofton Creek here. The main flow continued on down Salt Creek and left a deposit in a swampy area far downstream below tree line. But you can see how good the access is here. You can hike in on the Shorthorn Trail. You can hike in on the Round the Mountain Trail. Look at this debris flow channel. You can also come over and look at the big one. And then interestingly, if you keep walking, you'll cross some older debris flow paths. You can still see evidence here of in the morphology and the colors of these deposits. And then all the yellowish debris up above here is older debris avalanche deposits, probably larger from the 1921 debris avalanche that occurred on this side of Mount Adams. Okay, so now I'm going to move on to the next theme of my talk, which is larger debris flows that are associated with volcanic eruptions and large landslides and have affected the White Salmon and Hood River valleys. So first of all, looking at Mount Hood, this is a volcano hazards map for Mount Hood, a generalized volcano hazards map. In close, there are lots of diverse hazards. That's the kind of the bullseye here right around the summit of the volcano. But of interest in our current topic here are these downstream hazard zones along the courses of the major rivers. And you can see it on this hazard map. They're colored in two different colors. It discriminates DA from DB. You can see that along the Sandy River and the White River, it's both DA, this darker brown. And you can see that the flow path, the hazard area path along the Hood River is colored in this lighter shade, that's DB. The reason for that distinction is simply that there's very good reason to believe that future large lahars or debris flows from Mount Hood, at least in the foreseeable future, will likely go to the south rather than to the north. And the reason for that is simply that the crater of Mount Hood is open to the south, and recent eruptions from Mount Hood, one as recently as the late 1700s, and then a larger eruption about 1500 years ago, sent all of their debris to the south. And so really nothing very substantial in the way of large events has traveled down into the Hood River Valley for a long time, geologically speaking. That's also evident here on the geologic map of the Hood River Valley. This is a recent geologic map published in 2012 by the Oregon Department of Geology and Mineral Industries. It shows two large lahar deposits in the Hood River Valley, the so-called Hood River lahar, and then a second one called the Oak Grove lahar. Neither of these is precisely dated, but both of them are estimated to be roughly 100,000 years old. They're unquestionably older than the Missoula flood deposits here, which overlie them. And the Missoula flood deposits date from about 12 to 15,000 years ago. You can find these lahar deposits outcropping in a number of places. One of the more easy access places to see them in cross section is actually underneath the I-84 underpass at the east end of West Cliff Drive and Hood River. You can see what appear to be two distinct lahar deposits here, separate or with the boundary marked by the blade of this shovel. However, it's not entirely clear that these are actually two entirely distinct lahar deposits. They could be two phases of a single lahar. And in fact, it's even possible that these two different lahars are actually different phases of essentially a single lahar cycle. In any event, they're both old. We don't know exactly how old, but we know they're older than carbon dating, which can take us out to about 50,000 years. And we know that they're younger than certain other things that outcrop here in the vicinity, volcanic rocks and so forth. So big lahars have occurred here in the past. They've actually crossed the Columbia River, and deposits of these lahars can be found up along the road cut along the Cook Underwood Road. So it actually flowed partway up the White Salmon River Valley, but it happened a long time ago. And it happened with a volcano structure that was probably quite different from what we see today on Mount Hood. In contrast to that, at Mount Adams, there's been more recent, more significant lahar activity. And it's all come out of this area again that forms the head walls of the Avalanche and White Salmon glaciers. And most notably, only about 200 years ago, there was a significant lahar that originated in that area. It's mapped in purple here. My colleague Jim Vallance named this the Salt Creek lahar. And it did form deposits all the way down in the Trout Lake lowlands here. Although those deposits are not as extensive as those of an older lahar that occurred there about 6,000 years ago, called the Trout Lake mud flow. Both of these are of a size that I think a good way to think about these is that they're kind of in that same size category as that Mount Meager event that I showed you from British Columbia that occurred in 2010. That was about 50 million cubic meters. The Trout Lake mud flow is estimated to be about 66 million, and the Salt Creek about 15 million. So these are relatively recent geologic events. And it's certainly true that there remains a large quantity of that rather weak hydrothermally altered rock up here on this side of the summit of Mount Adams. So there is potential of this happening again. Because of that potential, USGS has done some further analysis of this situation using a statistically based method that we developed back in the 1990s, a method we call lahar-Z, or at least the computer program is called lahar-Z. And what it allows us to do is estimate areas that would be inundated by lahars of diverse sizes originating up in this quadrant of Mount Adams. Here you see a map view. This is an oblique view of the same thing, basically, zoomed in a bit. And so this spans a very large range of potential volumes, all the way from 1 million cubic meters up to a billion again being a cubic kilometer. So that's huge. That's so huge that I think it needs to be viewed as extremely unlikely unless there were to be a significant episode of volcanic unrest at Mount Adams, similar to what happened at Mount St. Helens in 1980. And that's probably unlikely because Mount Adams really has not shown much in the way of summit eruptive activity for more than 10,000 years. Recent eruptions of Mount Adams have been largely confined to lava flows around its flanks. However, you can see that this model prediction more or less matches what was observed from the Trout Lake and Salt Creek lahars that occurred here in the last 10,000 years. So there is some hazard in the Trout Lake lowlands. So the last theme that I'm going to cover briefly is where are we headed nowadays with regard to lahar hazard assessment, and specifically using models to refine our lahar hazard assessments. And the focus of most of that work for us thus far in the Cascades has been on Mount Rainier. And the reason for that is simply that Mount Rainier poses by far the largest hazard of any of the volcanoes in the Cascades. It's produced numerous large lahars in the past. It also has large populations living downstream in the path of prospective lahars. And so that's why it's received top priority, although we're just in the process actually of finishing up work on a Mount Rainier modeling study, and with luck, it'll be possible to move on to some other volcanoes before long. So here's a map showing a path of some of the large prehistoric lahars at Mount Rainier. Notably, as recently as 500 years ago, there was a very large lahar, 260 million cubic meters, that came off the west side of Mount Rainier, flowed all the way down the Puyallup River Valley, inundated the site of the current town of Ording. And that notably occurred without any evidence of accompanying eruptive activity. So presumably it was just a big landslide that happened, not unlike what happened at Mount Meager in British Columbia. An older and bigger lahar also occurred on the northeast side of Mount Rainier. Its path is shown here. This is the famous Osceola mud flow that was several cubic kilometers in volume. But this one was accompanied by eruptive activity and is so large that it's the sort of thing that would be highly unlikely to occur without some sort of major deformation of the volcano preceding the onset of the landslide in lahar. And at the same time as that occurred, there was another lahar that traveled down the Nisqually Valley called the Paradise Lahar. These have been known for a long time. A fellow named Rocky Crandall, the USGS, mapped these and published his map 50 years ago. So to develop a model of how lahars and debris flows behave, we've done a lot of experimental work. And I'm only going to show you this very briefly to make the point that to develop one of these models that uses physics to make prognostications, there's a lot of background experimental work, and those experiments are used to motivate the model and also in turn to test the model. To do experiments, we built this unique facility down at the H.G. Andrews Experimental Forest near Blue River, Oregon, where beginning in 1991, we started doing large-scale debris flow experiments. I'm just going to show you an example of a pair of experiments here of two identical debris flows released from the top of the flume. The difference between the two is that in one case, we just have a bare concrete bed, a bumpy concrete bed. In the other case, we've lined part of the bed with wet sediment. And you'll be able to see just how dramatically the presence of that wet sediment influences the behavior of the flow. So that's one piece of evidence among many that tells us that a really crucial factor in how these things behave is a process we call liquefaction, which is similar to liquefaction that occurs during earthquakes, but it's actually a bit different in its details. We've also used those same flume experiments to test predictions of our model. And here's an example of just one type of test where we did experiments where we caused the debris flow to run up a ramp here on an adverse slope. And then we modeled that same scenario in order to compare how well our model would do in calculating something that complicated. And it actually does pretty well. And that's the sort of thing that gives us faith that we can proceed with actually making prognostications for events at volcanoes. So I'm now going to quickly run through model simulations that we've done for Mount Rainier, specifically for the west side of Mount Rainier, from two prospective lahar source areas, one in the Sunset Amphitheater here, and the other at the Tahoma Glacier Cirque or Tahoma Headwall. These are the parts of Mount Rainier that have been identified as least stable, most likely to fail as large landslides by previous work done by my USGS colleague, Mark Reed, and others. So here's a simulation of a 260 million cubic meter liquefying debris avalanche occurring in the Sunset Amphitheater of Mount Rainier. You'll see just the first 2 minutes here in this clip. And you can see how it spreads out to some degree, but it largely gets funneled into just a couple of directions as it occurs. And then this next sequence of slides will show it advancing down the valleys away from the mountain. Notice that the scale here, this is 10 kilometers up here. So at this point, after 2 minutes, the leading edge has already traveled about 10 kilometers. And the speeds here reach about 180 miles per hour, which might seem outrageously high, but in fact, that's corroborated by observations of landslides where we actually, big landslides or big debris flows where we actually have constraints from seismic data or direct observation. So these things move really fast when they're on sufficiently steep terrain. The flow then carries down these valleys. Nearly all of it ends up in the main Puyallup River Valley. After 40 minutes here, it starts spreading out where the valley widens and slowing down. But after 50 minutes, it's right on the doorsteps of the community of Ording, which is a town of about 7,000 people, which lies entirely within the floodplain of the Puyallup River Valley. So it's really a place at considerable risk from this hazard. And then from there, we can model it further on downstream. We've also modeled a similar event originating in this other possible source area, the Tahoma Glacier cirque or head wall. And in this case, the initial avalanche actually spreads out and gets headed in a couple of different directions. And when we follow it downstream, we can see that it's basically funneled into two major valleys. One, again, is the Puyallup Valley. About half of it goes that way, but about half of it also goes into the Nisqually River Valley. At this point, it's already passed through the southwest entrance to Mount Rainier National Park. I'm sure a lot of you have gone through there. So that doesn't allow much time. That's only 10 minutes, and it's already reached that entrance. Within 20 minutes, it's already reached the town of Ashford. It's slowing down as it spreads out across the Nisqually Valley here. It's also traveling more slowly down the Puyallup Valley because there's simply less material here, less momentum than there was in that prior example. But as it continues down the Nisqually Valley, it eventually reaches the town of Elbe and Alder Lake Reservoir, and a lot of debris enters the reservoir. And so that's an issue of particular concern. Here's a clip showing the advancing lahar entering the head of Alder Lake Reservoir and displacing reservoir water. And here's an overhead view of the same phenomenon. In this case, it will actually illustrate mixing of the lahar material in brown here with the reservoir water. It mixes, but also displaces. And after about an hour and a half from the time of landslide onset, water begins overtopping Alder Dam, which is it's a big dam. It's 330 feet tall, concrete arch dam built in the 1940s. And it's beyond the scope of our work to do any sort of engineering analyses of dam safety, but we've certainly informed Not Pacific Power, I guess it's Tacoma Power, who operates the dam, who owns the dam. And so they're well aware of the situation here. And it's just one more part of the hazard story. So in closing, I've been talking a lot about hazards, and I don't want to leave you with the impression that our local volcanoes are all about doom and destruction. I certainly don't feel that way myself. In fact, I find them that they're much more a source of inspiration than they are of concern. And of course, the volcanoes are so important in terms of making the Columbia Gorge what it is. The scenery, the diversity, the interest of the place, so much of it is owed to the volcanoes and their downstream legacy, as well as the being up in the volcanoes themselves. So, and I guess it's also worth mentioning in passing, of course, that a lot of our important resources come from these volcanoes, not least of which is our water, much of our drinking water, much of our irrigation water that's so important to the economy here. So I don't think it's good to think of volcanoes in a one-dimensional sense, so that all they pose is threats and hazards. I think this quote from a poem by Pablo Neruda really summarizes the situation pretty well. And I feel like really the volcanoes are, I'm glad that I live where I do, close to the volcanoes. So with that, thank you for your attention, and I'd be happy to try to answer questions.
Thank you so much, Dick. That was great. And I appreciate you reminding us that you live here too. So if you've made the choice as well.
That's right.
Okay, folks, just a reminder, if you have questions, put them in the Q&A box and we will start ticking through them. Going back to when you were talking about lahars, you talked about the ice in them and the ice melts out and that changes how it lays. What about air in a lahar?
So air, so really what I was talking about was more the debris avalanches in terms of the role of the ice. Okay. And it's just a fact that because our volcanoes have so much snow and ice at their higher elevations, that usually where these debris avalanches start, they end up entraining or incorporating a lot of ice. And that ice does influence the dynamics to some degree, but ultimately it does melt out, and it leaves these somewhat perplexing deposits that I referred to as pancake deposits, because once the ice is all gone, the deposit looks so thin, and you think, well, how did this spread out this way? Well, the only reason it did is because of all the ice that it had in it. Once things reach the lahar stage, if a big landslide transforms into a lahar, usually by then, whatever important role the ice has played is already past, other than simply providing more water. And so a good example of the role of providing more water was from Mount St. Helens in 1980, where that huge landslide removed the north flank of the volcano, biggest landslide in recorded history. And it had huge blocks of ice within it. And during the hours after the emplacement of that landslide, that ice continued to melt. It was, to some degree, had some warm material around it. To some degree, it was probably just the heat from the landslide action itself. But that melting was partly responsible for forming lahars that then issued from that landslide deposit. So they're important. The ice is important as a water source for sure.
I want to go back to that final simulation you showed us. Someone asked, is it taking into account material eroded and entrained into the debris flow as it traveled along the debris flow path?
No, it's not. And that's actually a really good question, because from the standpoint of debris flow dynamics and hazards, entrainment is a really big deal. And
do you mind real quick explaining, since not everyone may know what entrainment means? Can you just—
Sure. So what it means is just incorporation of material along the way. So you imagine this mass traveling along, but it's interacting with the surrounding terrain and maybe causing collapse of riverbanks or slope failures or what have you. And so it can actually pick up a lot of additional mass as it travels downstream. And that really does have an important effect, but again, both in terms of the dynamics and the hazards. However, at this point, it's a really difficult problem from a modeling standpoint. Not so much, I'm kind of getting down to the weeds here, but it's a simple matter to simply stick terms in our equations. I mean, we can do that in 10 minutes and say, yeah, there it is. We've accounted for entrainment. But the hard part is, how do you constrain those terms? What are the physics you have to use or understand to say how much material is added? We can make something up, but making something up isn't very satisfying. So the short version of my answer is no, we don't account for it, but we realize that that's a shortcoming and a limitation of our model at this point.
Continuing on the idea of debris being picked up or being made more readily accessible to sliding, talk about the aftermath of wildfires. Is that increasing the risk of these slides in parts of the Cascades?
Yeah, absolutely. For those rain-triggered events, wildfire has a big influence. What's interesting right now is that it's seemingly becoming apparent. I mean, the quantity of data is not great at this point, but the interaction between rainstorms, wildfire, and debris flows in, for example, Southern California is really quite well understood at this point. What happens is the wildfire sweeps through, denudes the landscape of vegetation. The next big rainstorm comes, and all of a sudden you've got debris flows. But the way debris flows start in Southern California is very heavily influenced by the nature of the materials there. It tends to be granular, oftentimes material derived from granite-like rocks, so rocks that are really different from the kind of rocks we have around here. And it appears that with our kind of geology and our kind of vegetation here, that post-wildfire storm cycle, debris flow cycle is playing out differently. So, for example, within the Eagle Creek burn area, there was concern immediately after that fire that, oh boy, the next winter comes and we're going to have debris flows all over the place. And it just didn't happen. And partly that was because we didn't have any big storms that winter, any really big whopper storms. But since then, we have had some big storms. We have had some debris flows, including, very unfortunately, one fatal debris flow near Dodson in the gorge last January. but it's really been nothing like the kinds of scenarios they've seen in Southern California, for example. So we're still learning really how that whole cycle plays out here in the Northwest.
Okay, take the cycle all the way down to the river. What kind of impacts, and I'm not sure, maybe you need to be a fish biologist to weigh in, but I'll still ask you, what kind of impacts do these debris flows have on the Columbia River Basin, particularly in regards to cold water refuges for fish? So I guess it's all throughout the basin.
Yeah, well, certainly in the, in the Columbia River itself, I'm not sure that they have a great deal of influence, but certainly in the tributaries, the Hood River being a good example, or the White Salmon River. When a sizable debris flow comes through, it completely rearranges the channel and rearranges the placement of the woody debris. Maybe creates pools where there were riffles and riffles where there were pools. It really changes everything, and it always amazes me, that fish runs can withstand the impacts of sizable debris flows. But even at Mount St. Helens, where the Toutle River system just got, sort of annihilated by the eruption in 1980 and subsequent debris flows and so forth. Fish have returned there too. And so they, I guess the way I think about it is that this is a natural phenomenon, this kind of rearrangement of the channels, and the fish have co-evolved with this. And so this is something they have learned. I'm using the term learned loosely here, but this is something they can handle. Whereas some of our human impacts, they have not co-evolved with.
Okay, let's see if you can identify something. The point where Salt Creek joins Cascade Creek, about 3,000 feet, there's a broad debris flow, which I assume closed the trails there. When did that flow happen?
So I think that's where the deposit is of the 2006 Salt Creek debris flow, and that's in sort of a meadow, a boggy meadow, basically where Salt Creek joins Cascade Creek. So I'm pretty sure that's what's being identified.
Okay. Someone wants to know, is it true that Houston Falls is the toe of a debris flow, and if so, when did that debris flow happen, and which toe is it? No, I'm just kidding. I put that part in.
Boy, that I absolutely do not know the answer to that question.
Okay.
I've always assumed, just driving past, I've always assumed that Houston Falls was due to an outcropping lava flow, but maybe I'm completely wrong.
Okay. Okay. Check if you hear differently. If you learn anything in the future, just let us know.
Okay.
We'll let folks know. Okay. Someone's wondering, talk about how the Missoula floods, would they have been anything like a debris flow? They're obviously going to have debris in them. So compare and contrast.
Yeah, that's an interesting question, because probably the closest thing we can use to help us imagine what the front of the Missoula floods might have looked like is some of the video that was taken during landfall, the Tohoku tsunami in Japan back, I can't remember how many years ago it's been now, probably, at least half a dozen, maybe 10 years ago now. But if you saw some of that video footage, it was incredibly dramatic. It was this wall of water, coming on shore. And of course, this was a tsunami, but, kind of like a flood. And it picked up everything in its path. It picked up ships, it picked up cars, houses, you name it, and just swept them in front of it. And so the leading edge of that tsunami looked a heck of a lot like a debris flow. And I think it would be the same way with the Missoula floods. Although a caveat with the Missoula floods is because they occurred in relatively rapid succession, one after another. There probably between floods wasn't a lot of opportunity for things like vegetation to grow back. I'm not sure. It might have been, and it was post-glacial or in glacial times. It was probably a somewhat desolate landscape at the time.
I'm curious, if I was just out hiking around or walking around, we'll often look as a family and try to help our kids learn and say, okay, that must have been, these are layers from the Missoula floods, or this is, whatever it is. What would I look to say, what would I see if I looked and said, okay, that's not Missoula flood, that it was obviously an old debris flow? Like what are the characteristics of it that are different?
That's a really good question. So the key characteristics are that flood deposits are usually to some degree stratified, meaning you can see layering within those deposits. And usually the sediments are fairly well sorted, meaning that it'll be a pocket of basically all sand or all gravel, but everything's all kind of the same size. Whereas in a classic debris flow deposit, it's completely unsorted, meaning every range of particle size you can imagine, all kind of mixed together, everything from specks of clay to big boulders, and also no stratification, what geologists call a massive deposit, where it's just kind of one big thick layer. So yeah, so to a practiced eye, they're pretty easy to tell apart. What's sometimes not so easy to tell apart is the difference between, for example, glacial till and debris flow deposits. And there are a lot of classic cases where people had mistakenly identified something as till when in fact it was a debris flow deposit.
Let's see, as the glaciers decrease in size, how does that affect the occurrence of debris flows?
So my personal feeling is that here in the Cascades, the glaciers have already diminished sufficiently in size that they've already exposed so much loose debris around their moraines and so forth that further reduction in the size of the glaciers probably isn't going to influence the debris flow potential that much. Now, in other parts of the world, that's different. For example, where some of the big glaciers have been withdrawing in the Alps, like in the Swiss Alps, they've been removing buttressing or support from some huge moraines of loose material, and so they're getting increased incidence of debris flows and so forth. But most of our glaciers at the Cascades volcanoes simply aren't that big and really aren't providing a very major buttressing role. So I think that's kind of a situation where the horse has already left the barn.
Maybe this is a dumb question, but at some point, do these volcanoes, all the loose stuff that's on the outside, flow down and we're left with just hard rock that's not gonna, the flows are done. The material has been flowed and we are just gonna have thin, pointy old mountains?
Well, I guess we sort of have some examples of that in the Oregon Cascades. Things like Mount Washington, Three-Fingered Jack, to some degree North Sister, where they're just kind of pinnacles of rock. They've got some debris around them, but nothing like Mount Hood or Mount Adams has. So in those cases, then those are usually considered to be extinct volcanoes, which certainly is not true of either Mount Adams or Mount Hood. They're very much active volcanoes that could rumble to life at any time. And I don't think any geologist would expect someplace like Mount Washington or North Sister to suddenly spring to life as a eruption source.
Okay, I've got a question. Someone says, I was surprised to see lahars from Mount Adams are more likely to follow the Trout Creek watershed than the white salmon initially. Why is that? And how long would it likely take for a lahar flow to get to Trout Lake, which seems to be directly in the lahar danger zone? And are there early warning systems in place anywhere that are valuable? I'm guessing this may be a Trout Lake resident asking.
It sounds like a maybe. So I think the path they take is really just a consequence of where they originate. And if it were a big enough avalanche high in that White Salmon Glacier, Avalanche Glacier, it would probably actually end up entering several different drainages, all of which would eventually funnel into the White Salmon, but it would start out down different drainages. I think it's just that the more recent ones have tended to focus more towards Cascade Creek and so forth. But that's to some degree I think a matter of accident, really nothing profound about that. In terms of timing, I can't, the thing is the timing is contingent on the size of the event. The bigger they are, the faster they move. But I think, you can make some estimates based on what has happened elsewhere. And I'm not going to name a number, but I guess what I would say is, look at some places where information on timing has been published. And for example, that hazard map that I showed you for Mount Hood, that USGS hazard map, that shows some timing estimates down the drainages for big lahars that could potentially move down those drainages. And I think that the speeds would be similar at Mount Adams.
Are there early warning systems in place anywhere?
There's only one place in the United States that currently has an early warning, or at least in the lower 48 states that currently has an early warning system, and that's along the Puyallup drainage at Mount Rainier. And again, that's been identified as really the area at greatest risk of any place in the lower 48, and that's been a long developing process. But there is a warning system in place, and the community there actually practices evacuation drills and so forth when trial warnings are issued or sirens are sounded. A lot of it, and I think any place where there's a warning system installed, that needs to be part of the protocol. There needs to be a lot of practice, because a warning without knowing exactly what you're going to do in the advent of a warning really isn't very useful. And the basic rule of thumb is just get to high ground. These things, they're like floods in the sense that they follow the low ground, and if you have high ground anywhere nearby, just try to get to high ground.
Can earthquakes start debris flows?
They can certainly start landslides, which in turn can transform into debris flows. So yes.
Okay. Did the breaching of the Condit Dam provide any insight with all of the sediment released?
Yeah, that was actually really interesting. And I'm thinking not so much of the sediment flow downstream from the dam breach, which actually it did. I mean, there was a lot of sediment in the river there for a while following the dam breach. But what was actually more interesting to me is that upstream in the reservoir, as the reservoir drained, there was all that mud that had accumulated over the many years on the bottom of the reservoir. And as that material started to dewater, it started to flow away in large chunks, basically, sort of partially liquefying and flowing away, and becoming something sort of like a slow motion debris flow. So that was a pretty fascinating sequence of events.
I had someone tell me once that geologists have to be really good at telling stories, since geology is, the timeline's so long. But I feel like you've chosen a field where you can actually see the story happen sometimes too, which is
yeah.
great.
Well, I've always, from the very beginning, I've always been interested in geology of the present rather than geology of the deep past, just because I guess it's just more interesting to me.
Let's see. Someone's wondering, scattered around the Trout Lake Valley are large boulders that are sitting or sort of jutting up from the flat landscapes. Were these rocks deposited in lahars?
Yes. That's a simple answer. Yes.
There you go, Caitlin. That's a yes. Let's see. I saw another one that was, okay. Another one about location and rocks. Was the area around Rocky Road and Hood River part of a lahar? It has tons of boulders. I don't know if you know where that is.
I don't know exactly where it is, but is it in the Rockford neighborhood?
I'm thinking the section of it I know is out going from May Street towards West Side Elementary. Peter, if that's the spot you're thinking of, let me know, but that's the spot I'm aware of. So we'll come back to you. But I think that area, I don't know if you know where West Side Elementary School is, and then it goes to May Street, and then there's a sort of a green space. Yeah,
I'm thinking that's probably so. Yeah, I'd have to look at the geologic map in detail, but I think that is probably an area that maybe is not lahar deposits. Rather, those are just blocks of lava flow, that have kind of weathered out in place. And, one could determine that by looking at the rocks. The thing about one way to discriminate a lahar deposit, say coming from Mount Hood, is that the rocks themselves will be Mount Hood rocks, and Mount Hood rocks can be discriminated from those of the lava flows that form some of the landscape closer to the river in the Hood River Valley. So there's different rock types.
Going back to sort of the characteristics we would see in a flood deposit versus debris flow, a fellow geologist is saying, would the debris flow also have more angular rocks versus more rounded in a flood deposit?
Yeah, I mean, I think on average, yes, there are probably always exceptions to that. The thing is, because debris flows often entrain a lot of river rocks from the channels, they end up carrying a lot of rounded rocks too. So what I would look for more in probably a debris flow or lahar deposit is a diversity. You know, some rocks well-rounded, some angular, a little bit of everything really. Whereas it is true that a classic river deposit would have a much higher concentration of purely rounded rocks.
Looking at changes in climate, what's your opinion about the likelihood of future catastrophic sort of rain on snow events like the ones in 96, 97?
Well, I'm not a climatologist, but I mean, the climatologists do seem to agree that, you know, big storms, atmospheric rivers, that sort of thing are going to be perhaps more common in the future. The other thing that I think about in terms of the debris flows from the volcanoes is that as our snowpacks diminish, and that, you know, as a skier, I can see that diminishing before my eyes. You know, I mean, the snowpacks here aren't what they were 30 years ago, that's for sure. You know, that through the course of the winter, we're going to become more and more vulnerable to those rain on snow events that trigger debris flows only when you have a relatively thin snowpack. So in other words, we'll lose some of that protection from a deep snowpack.
We've got a couple more questions that I want to get to in a second. Dr. Iverson, we've got someone curious if it's possible to go back in your slideshow to show that first debris flow. While you do that, I'm going to remind you guys that we have Sense of Place next month, January 12th, native bees of the gorge. Did you know we have native bees? Do we have more than one native bee? How do they fly with all their little wings and their chubby bodies? What sort of plants did you put in your garden? All kinds of stuff about native bees in the gorge and pollinators. That event will be virtual again, but I want to give you a heads up that we're looking to February, March, and April, possibly being live. We're working on final details to see if we can make that work. But we're also working at the same time on, if we go live, can we also still do a video or live stream presentation? So stay tuned to the website. We're doing the best we can to figure this out with all our partners and our speakers. So tune in next month, though, January 12th, for Native Bees of the Gorge. Okay.
So I'm not sure which one is the first.
I think it was the very first video you have.
First video.
Yeah, Indonesia. So while you go to that, I'm going to ask you another question too. Let's see. That'll be the one. Hold it. We're going to show that at the very end before we go.
Okay.
Someone's wondering how much precipitation drove the 2006 debris flows on Mount Adams. And then, oh, go ahead.
Yeah, well, so we don't have the same degree of instrumentation high on Mount Adams. You know, in Mount Hood, we benefit mainly from the rain gauges, for example, up at the ski areas where you're measuring rainfall, you know, at 5,000 or 6,000 feet elevation, and we simply don't have gauges like that on Mount Adams. But I think there's every reason to suspect that the rainfall pattern at Adams was very similar to that on Hood, simply because the debris flow pattern was so similar. You know, so I'm guessing that over the course of those several days, there was, you know, on the order of a foot of rain at elevations of 6,000 or 7,000 feet. And I think that would also be borne out true. You know, another place we have higher elevation data is further north at White Pass and also at Mount Rainier at Paradise. And those areas too received similar amounts of rain. So it really was regional in scope at those elevations.
Okay, one last question before the video. Any research on the interactions between lahars and the possible creation of fish habitat. So thinking about gravels and wood supply.
Yeah, well, again, the harvest debris flows, they completely rearrange stream channels. And I think, from a fish standpoint, they probably do some good things and some bad things, depending on where you look. But my view, taking a very long range perspective, again, the fish co-evolved with these events, and they seem to be able to handle them. It might take them some years to recover in a channel that's been hit hard, but I don't think that if we're looking for causes of diminished fish runs, I don't think debris flows are a likely cause.
Maybe we can give them some credit sometimes too for bringing in some good fish housing.
Right.
Well, I want to thank you before we play this last video, and hopefully it's Axel, who is a 5-year-old who really wanted to see this video. He must not have gotten to see it. So thank you. Before you play it, I just want to say thank you so much for joining us, for making geology come alive tonight. I will definitely look around at things a lot differently on my next hike and drive. And maybe I'll see you around in town sometime. So thank you so much. Thank you everyone who tuned in. Happy holiday time. We're going to watch a debris flow and then you can go to bed. Take care.
Here we go.
Tu peux te pousser, monter un tout petit peu s'il te plaît?
All right. Bye, everybody.